In this video, we're going to write and solve the Schrödinger equation for a particle in a 1D box. This is the box in question here. It extends from 0 to a on the x-axis. And we're going to divide the x-axis into three regions for our purposes here. The first region is x less than 0, which is to the left of the box. The middle region is the box itself, x between 0 and a, which is here, and the third region is x greater than a, which is to the right of the box. For these three regions, the potential energy is going to be infinite outside the box, which means x less than 0 over here, or x greater than a over here, but 0 inside the box in this region. That means that the wave function will be 0 for x less than 0, and will be 0 for x greater than a. And what we want to find then is the wave function in this 0 to a region. So that means that v of x is 0, between x is 0 and a. The wave function is what we're after, and therefore the potential energy operator is going to be 0. The Hamiltonian operator, which is normally the sum of the kinetic and potential energy operators, is just going to be the kinetic energy operator. We're also going to have two boundary conditions shown here. Psi at x of 0 is going to have to be 0, and psi at x equals a is also going to have to be 0 because the wave function is 0 outside the box, and it has to be continuous. So the Hamiltonian operator is the kinetic energy operator. In this case, it's one-dimensional. Because the kinetic energy can be expressed as the square of the linear momentum divided by 2 times the mass, we can construct this operator using 1 over 2m, where m is the mass, and the linear momentum operator twice. The linear momentum operator is negative I h bar derivative once with respect to x. And so with two of these linear momentum operators, the negatives are going to cancel. We're going to have 2 i's, or I squared, which will give us a minus 1, 2 h bars, which is going to give us an h bar squared, and then the derivative of the derivative will give us the second derivative. And so our kinetic energy operator is negative h bar squared over 2m, second derivative with respect to x. Now that we have the Hamiltonian operator for this particle in a 1D box, we're going to operate on the wave function with it. And the result of operating on the wave function with the Hamiltonian is then going to be the energy times the wave function back. This gives us a differential equation, an equation which relates a wave function to its second derivative. And to find the wave function, we have to solve this differential equation or find the mathematical form of psi of x. Before we solve this differential equation, let's rearrange it a little bit. Let's start by subtracting e times psi of x from each side. On the right-hand side, those cancel out, and so we get 0. Next, let's multiply each term on the left-hand side by the same constant, negative 2m over h bar squared. The result of that is that the m's cancel from the first term, the 2's cancel from the first term, and the h bar squareds cancel. Negative times negative gives us a positive, and so the first term only has the second derivative with respect to x of the wave function psi of x. The second term, the negatives cancel, and what we find now is that all of the constants, the 2, the mass, the energy, and the h bar squared, all of the constants are grouped in the second term. So now the rearranged form of the differential equation that we need to solve looks like this. If we replace the 2me over h bar squared with k squared, the differential equation looks like this. This is a linear, ordinary differential equation with constant coefficients, and because those constants are real and positive, k squared is also real and positive. The general solution to this wave function can be written as a sum of a sine and a cosine with two constants, capital A and capital B. The k is related to k squared equals 2me over h bar squared, but the capital A and the capital B are undetermined constants at this point. So here's our general solution. Here's our expression that tells us about k. Now we need to bring in these two boundary conditions and use those to determine some of the other constants in this general solution. So our first boundary condition says that psi at x equals 0 must equal 0. And to apply that boundary condition to our general solution, we'll take x equals 0 and substitute it into our general solution into the cosine and sine terms. That will give us a cosine 0 plus b sine 0. Sine of 0 is 0, but cosine of 0 is actually 1, which gives us a plus 0. So this first boundary condition then doesn't put any requirements on the value of b, but in order to satisfy this boundary condition, this capital A constant is actually going to have to be equal to 0. Our second boundary condition says that psi evaluated at x is a must also be 0. So we can substitute x equals a into our general solution and have a cosine of k times a plus b sine of k times a. We now know that a is 0, and so that zeroes out the first term, but we still have the capital B in the sine term. To see how we can satisfy this boundary condition with b sine of k times x, let's look at a plot of a sine function. Here's a plot of sine of kx as a function of kx, and what we want to do then is have sine of ka equals 0 somehow. Well, if we look at this, what we notice is that sine of kx equals 0 when kx is 0, or pi, or 2 pi, or 3 pi, or any integer multiple of pi. And so sine of k times a will equal 0 if we have k times a equals n pi, where n is some integer 1 or greater. So going back to our general solution, we now know that the first boundary condition means that capital A must be 0. The second boundary condition actually means that k has to be n pi over a, where n is a positive integer starting at 1. If we put these things together, we get a solution that so far looks like this. Notice that we have appended a lowercase n, that integer here, to the symbol for the function that we're trying to find, the wave function depending on x that we're trying to find. The reason we've done that is that we actually have a family of solutions, one solution for each possible value of n. That n is actually a quantum number, and we have a family of solutions to our differential equation, one for each value of n. We still don't have anything for capital B, however, and we'll return to that. So now we have two expressions involving k. The first one is that k is equal to n pi over a, that allowed us to satisfy the second boundary condition. And the other is that k squared is 2 times the mass times the energy over h bar squared. K squared was the abbreviation for this collection of constants that we used in writing the original general solution to our differential equation. So now let's square this left-hand side expression. That gives us k squared equals n squared pi squared over a squared. And now we have two expressions that should be simultaneously true. We have this one for k squared, and we have this one for k squared. N is our quantum number, pi is a constant, a is the length of the box, 2 is a constant, m is the mass of the particle, h bar is a constant. E, however, was introduced in our original Schrodinger equation. And so what we can do then is set these two equal to each other and multiply by some constants. H bar squared now cancels, 2 now cancels, m cancels, leaving only the energy on the right-hand side. And the energy, therefore, must be equal to this collection of constants, and therefore it has a different value for each value of our quantum number n. We can simplify this a little bit by replacing h bar squared. If we separate that out and replace h bar squared with the h over 2 pi that it stands for, that allows us to cancel out this pi squared and the pi squared inside the parentheses, and we can then simplify our result for the energy to look like this. E, the energy for a particular value of n, the quantum number, is n squared, h squared, no more bar, 8ma squared, where the 8 is the 2 and the 2 squared that we had up here. So this is the energy for each value of the quantum number n that goes with the wave function, which also has that quantum number n in there. So now we have this form of our wave function, which is the solution to the Schrödinger equation. We know what n pi, a, and x are, but we don't know what b is. We have our energy, which also depends on n, as well as h and m and a. But what about this capital B? How are we going to find this capital B? We're going to find the value of the capital B constant by requiring that our wave function be normalized. Normalization means that if we take the integral over all space of psi star times psi, that we should get 1. And that's because integrating over all space is adding up all the probability of finding the particle that's described by this wave function, and the probability of finding it anywhere should total 1. In order to use this to find our capital B, we're going to separate this integral into 3 parts. The first part is from negative infinity to 0. The second part is from 0 to a, and the third part is from a to infinity. And the reason we did that is that the wave function at x less than 0 and at x greater than a is 0. This wave function here, its complex conjugate, are both 0. This one we're trying to find. And this one here then is also 0, as well as its complex conjugate being 0, which means that really it's the integral from 0 to a of psi star psi that has to equal 1. So let's work on this integral. We know that psi of x is capital B sine of n pi x over a. That's here. Psi star indicates the complex conjugate of that same wave function, but sine of n pi x over a as well as b are all real, and so the complex conjugate is actually equal to the wave function, and we can just write the square of the wave function. B is a constant that we're trying to find, so we can factor that out of the integral because it does not depend on our variable x. The result of this integral looks like this. We have carried the b squared along. The integral gives x over 2 minus a sine of 2 pi n x over a divided by 4 pi n. We need to evaluate this at a and at 0. Evaluating it at 0 is going to give 0 for this term, as well as sine of 0 gives 0 for the second term. Evaluating at a is going to give a over 2 for the first term, and a sine 2n pi over 4n pi for the second term, where evaluating at x equals a caused these two a's to cancel. At this point, we also need to recognize that sine of an even number of integer pi's is going to equal 0, and so this entire second term equals 0, and what we have left then is 1 equals b squared a over 2. We can solve that for b, which is what we're after, by multiplying both sides by 2 over a. Then the a's cancel and the 2's cancel. We'll take the square root of the b squared, and that will give us then that b equals the square root of 2 over a. So we find the value of this constant is related to other constants that are already in our general solution. So here's the solution we had for our wave function. Here's what we just determined for the capital B constant. If we substitute those in, our wave function then, properly normalized, looks like this: square root 2 over a sine of n pi x over a, where x is the independent variable, a is the length of the box, pi is a constant, n is that quantum number that we found we had to bring in to satisfy that second boundary condition, and that is our complete solution. Returning to our box, recall that we divided our x-axis into 3 regions, shown here, because of the potential energy. The wave function outside the box is 0. We were looking for the wave function inside the box. So the wave function looks like this, with the requirement that n is a positive integer 1 or greater, and the energy that goes along with each wave function is given by this formula here.